Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and I have another tutorial in our series on sequences and series. And today we're talking about infinite geometric series. In the last two videos we talked about arithmetic and geometric series, and on those we were adding up the sum of a fixed number of terms. So those were finite series. Today we're talking about infinite series, meaning we'll add up the terms an infinite number of terms. For some geometric series, we can add an infinite number of terms, but have the answer approach a finite number, a fixed number. It's a little weird that we can add up an infinite number of numbers and have the sum be a finite number. Series that have those properties are called to converge. Other geometric series, if we try to add up all the items in the series, the number or the result you get will be infinity. And in this case, that type of series is called to be a divergent series, or that it diverges. Now, the way we can tell if a series will be convergent or divergent is by looking at the common ratio. If that common ratio is less than 1, now the absolute value of it, so if it's between -1 and +1, then the series will converge. If the common ratio is 1 or bigger, then it will diverge. The formula we can use to calculate what that sum would be of that infinite number of terms is given here. So we're taking the first term and dividing it by 1 minus the common ratio. In the last tutorials we had S sub n, where n was the number of terms we're adding up. In this case we're not putting a number here, it would be infinity. And again, this formula is only used if the absolute value of the common ratio is less than 1. Other types of series, for example arithmetic series, if you try to add an infinite number of those, they will never converge. So before we work some sample problems, let's just kind of visualize why this might be the case. So we have a geometric series here where each term in the series is multiplied by 1/2. So based on what we had on the last slide, this series, if we keep adding, would be a finite amount. So let's put the first term, let me split this circle in half. So this is our representing our 1/2. So that's this part. And now the next term is half of the previous amount. So that's going to be a 1/4. And the part that's shaded is the sum. So right now when we add those two terms, we've got 3/4. Now we add half of this piece. I didn't quite divide that in half, but you'll get the point. It's 1/8. If we add the next term, it would be 1/16. And then we would add half of that. And you can see we're always going to have a little bit of a wedge left, and we can keep adding half of that, dividing it by half, so we will keep getting closer and closer and to fill up the circle. So for this, based on the picture we just drew, this geometric series, if we added up, the infinite number of terms would add up to be 1. Let's look at our formula. S equals a sub 1 over 1 minus r. And in this case, our initial term was 1/2. And we've got that by 1 minus 1/2, which is 1/2 divided by 1/2. And in our recent lesson about complex fractions, we turn this into the top times the reciprocal of the bottom. Our 2's cancel and we get 1. So you can see visually how that arrives at 1, and now we can see with the formula how we would get the same answer. So let's look at some sample problems like you'll see on your practice worksheets and your exit tickets. So the first part, all we're trying to determine, does it converge or diverge? We don't need to give the answer at this time. So we have to figure out the common ratio. So 2 to 1, we're multiplying by a half, we're multiplying by a half, we're multiplying by a half. So in this one, the common ratio is 1/2, which is less than 1. So this series would converge. My handwriting there was bad. Converge. Here, going from here to here, we're times by 3, times by 3, so it is a geometric series. And our common ratio is 3. That is bigger than 1, so this series, if we added it up, would diverge. Now let's look at two examples here where we want to actually compute the sum. So first we have to compute the common ratio. So in each of these fractions we are multiplying by, on the top, by 2, because this is over 1. So the tops are doubling and the bottoms are being multiplied by 3. And we are alternating signs, so our common ratio is -2/3. Now the absolute value of that is less than 1, so this one will converge. If we have a problem like this and our common ratio is not less than 1, don't use the formula. You'll get a number, but that number will be incorrect. You would just write that there's no sum or that it diverges. So here we can plug into our formula. S equals a sub 1, which is 5, divided by 1 minus -2/3, which is 5 divided by, this would be 1 plus 2/3, which is 5/3. Turn that into the top times the reciprocal of the bottom. Our 5's cancel out and we get 3. So if we kept adding this up forever, we would get the positive number 3. And here, each of these terms are dividing by 5 or multiplying by 1/5. So our common ratio is 1/5. Again, that is less than 1, so this does converge. So we're allowed to use our infinite sum formula, a sub 1, which is 31/25, and 1 minus 1/5, which is 4/5. So we've got, if we simplify our complex fraction, 31/25 over 1 times the reciprocal of the bottom, which would be 5/4. And if we multiply that, we've got here, let's see, that's 25, 10, carry the 2, so 126, 15, 625 fourths. So that would be our result here if we added all these numbers, an infinite number of them. Now we could divide this out and get a mixed number if we want, but we'll just leave it as that fraction. So you can see infinite series are pretty easy. We just need to remember to verify that the common ratio, its absolute value, is less than 1. Have a great day.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you